the first thing, when you talk about free body diagrams, it's basically representation of force. So what are you trying to do here? Now let's discuss the cases individually. When the lift is accelerating upwards quickly, so this is called the triangle law of vector addition. So where I have placed two vectors such that the first ends here. What if some vector is inclined to our standard x-axis and y-axis, right? Normal contact force you would always visualize as a pushing force, while tension is a force that develops in a string. Hello students, welcome in today's class. In today's class, we are going to continue with the unit forces, where we have discussed a lot about forces already, like what do you mean by force, what changes can force make, what are the various types of forces, and also an introduction of momentum and impulse. So we are continuing with that series, and today, most importantly, we will continue with the concept of tension force. So that was done in the previous classes. We had discussed what is tension. It is a pulling force that develops in a string in the presence of an external force, right? So today we are going to start with that straight away with numericals, which are very important and you can very much expect them in the exams, right? So we will start with simply a problem including not only a string but also a pulley, okay? So this particular question is very important to form the foundation of pulley related questions. Alright, so first you write down the question, you look at the question, and then we will start with the solution. Alright, so this is the question. Find the tension in the string and acceleration of the blocks. Assume the pulley to be frictionless. Okay, so for now we are assuming that there is no friction on the pulley. So you are aware of what pulley is. You have a pulley arrangement, a simple pulley or Atwood machine, and there are two blocks, obviously unequal masses. If they would have been equal masses, then they might balance each other, right? But they are unequal masses, and therefore we don't expect this system to be in equilibrium, right? So let's say this is 3 kilogram, this is 2 kilogram. Think about it. We will draw the free body diagram that we had discussed in the last classes, that what is a free body diagram. For now, I am drawing the free body diagram in this particular diagram itself. You can do it separately also. Okay, so first, the force acting in the downward direction is because of gravity, while the string is always going to apply a pulling force. We are assuming there is no friction, so the same tension is going to be there in the string on both the sides. So when we draw the free body diagram of this, it's going to be mg, that is 3g in the downward direction, and again the tension force acting in the upward direction. Are you able to correlate with this? Did you also think in this fashion? I hope so. Okay, now we are assuming that this system will descend, like 3 kilogram will descend and 2 kilogram will ascend with the same acceleration. Now, why would we think that way? Because the string we always assume is inextensible. It cannot change its length. Hence, if this descends by a distance x, then this also has to ascend by the same distance. That is how you use pulleys, right? You pull the string on one side and you expect the other side to rise. Okay, now let's revise. What was Newton's second law? F is equals to ma. But the thing here is that 3 kilogram is going downwards while 2 kilogram is going upwards. So let's write it for 3 kilogram first. Alright, so what is it going to be? So it will be 3g minus t equals to 3a, isn't it? 3g minus t is the net force downward, and that should be equal to mass times acceleration. Okay, while for 2 kilogram, what are we going to write? We'll write t minus 2g equals to 2a. Now why this change? Because this is ascending while this is descending. So for this one, the net force is going to be this minus this. Okay, now we have the two equations and we have two variables. We don't know what is the acceleration and we don't know what is the tension. So let's add the two equations. let's call it 1 and let's call it 2, and let's add these two equations. So what are we going to get? G equals to 5a, or a equals to g by 5. Since in the problem it is given that let's take gravity as 10 for calculation convenience, so it's going to be 10 over 5, and that's going to be 2 meter per second square. And if we put the value of a, we get the tension as 2g, that is 20 plus 2 times 2, and that is going to be 24 Newton. So it is in continuation of the questions that we had done in the previous classes. So it is recommended that you are going to watch this particular class if you already have watched those classes. Okay, this is very important. How are we operating, how the forces are operating, and how Newton's second law applies in situation when the system is not in equilibrium. These cannot be referred as in equilibrium because they are accelerating. Okay, so now you understand how a pulley can be involved along with the string? Of course, yes. Okay, and you know the value of T now, and you also know the value of A. Okay, copy this down, try to solve the next numerical first and then only look at the solution. But first copy this down, I will wait, you grab a screenshot, then we move forward. Alright, so you must have taken a screenshot of this. This is another question for you, again very exciting. Very quickly, let's revise what we have already talked about. So let's say there is a triangular block, okay, of an angle theta. So we can call it a wedge, we can call it an inclined plane, and now there is a block of mass m, let's say, placed on this wedge. Okay, so if you remember in the last class we have talked about it, that gravity is going to act in the downward direction, right? But then we were interested in knowing its components. So how do we take the components? Let's change the color here. Let's say these are the components. The component of this along the inclined plane is going to be mg sine theta, while the component of this perpendicular to the plane was mg cos theta. This thing, how? Because if this angle is 90, this has to be 90 minus theta. Pay attention, we are revising again. And if this is 90 minus theta, then this again will be theta. And since this is theta, the component of a force along another direction, let's do that. Let's say this is a force F and these are the two axes, let's say. And this force F makes an angle theta with the given axis. Okay, so what are we going to do here? Let's say this component of F, let's say, is going to be F cos theta, while the component of this is going to be F sin theta. Now, what do you mean by components? Instead of F, you can show these two forces. They will play the same role as this F. That is what vector resolution was all about, which we have discussed in the previous classes. That is obviously going to be used here. And again, the wedge is frictionless. There is no friction on the wedge for now. Now, let's do this. Let's draw the free body diagram. So this is the first thing that you do. The force acting downward is the force of gravity, and then the force of tension. So as we know, tension or Ft always acts in the direction of the rope, and it is always a pulling force. Now think about this. There are two things. Whether this will fall or this will descend, we are not sure, because this is 2 kilogram, this is 3 kilogram. Now do you think that 3 kilogram will fall because it is heavier, or 2 kilogram because it is lighter, it should rise? Let's find out. So let's draw the free body diagram of this. So tension is acting along the string as you would expect, and the force taking it downward is going to be 3g sine theta, that is mg sine theta. Now let's do this. This value of g is 10 and theta is 30 degree. So if we do this calculation, 3g sine 30, then it's going to be 3g over 2. Okay, so 2g and 3g over 2, which one is bigger? 2g. Hence, in spite of this being the heavier block, instead it will rise. Why so? Because it is not the entire gravitational pull of the earth that is pulling it down the incline. It is only the component of mg, which is the mg sine theta component, that is pulling it down. So even if you assume wrong, let's say, even if you assume that acceleration, this is upward and this is downward, automatically your value of acceleration will turn out to be negative, which means that whatever direction you have assumed is wrong and it is opposite. Okay, so just like in the previous problem, I had assumed that this is ascending and this is descending, and that is why 3g minus t was equals to 3a for this one, and t minus 2g equals to 2a for this one, and I solved the equations, right, because this was going up and this was going down. If I had assumed the opposite, that this going down and this going up, automatically my value of acceleration would turn out to be minus 2, which means that there's no problem, just that what I have assumed is the wrong direction. Okay, all right, so where were we? We were talking about this. Let's do this now, that the acceleration of this is a downward, let's say. So this is 2g minus t equals to 2a, because it is going downwards. So this minus this equals to 2a. That is how pulleys are being involved. Again, we are assuming pulley to be frictionless. So the string can pass over the pulley and still same tension can be maintained. Okay, you must have seen pulleys everywhere around you. How do they function? But every time you see such pulleys, they obviously have some friction, and that is why when the masses move, the pulleys have a tendency to rotate. But we are not assuming that for now. We are always assuming the pulley to be frictionless. Okay, then we will also discuss what happens when friction is there. Okay, what about this one now? So for this one, we are going to write t minus 3g sine 30, that we have already calculated is 3g by 2, and that is equals to m times acceleration. So the mass of this is 3 kilogram. So t minus 3g by 2 equals to 3a. Let's add the two equations. What are we getting? G by 2, since t and t cancels out, equals to 5a. So a turns out to be g by 10, and we are taking g as 10 already. So this value turns out to be 1 meter per second square. So this is going to fall with 1 and this will rise on the wedge with 1. Again, heavier is rising, lighter is falling, because it's not the entire gravity which is acting here pulling it down. Put the value of A, the value of tension turns out to be 20 minus 2, and that is 18 Newton. Just to make you more comfortable, we'll do more questions like this, but after every question you should evolve and understand more of these kind of situation. Copy this down, then we move forward. All right, so let's look at another interesting question. Again, it's a pulley block arrangement, as you can see, but instead of the block, now we have a person or a man here, right? Try it first, I will wait, and then we move forward with the solution. Okay, so figure shows a person in an elevator pulling on a rope that goes over a pulley and is attached to the top of the elevator. The mass of the elevator is 30 kilogram and that of the person is 70 kilogram. Okay, T again we are taking as 10 for calculation convenience. Okay, draw the forces on the person. So let's say this is the person and this is the elevator. Okay, let's draw the free body diagram. Let's do it separately this time. Okay, so this person, are you able to imagine what is happening? The person is pulling onto the rope, and because the rope is shortening, this elevator is rising, right? That is what is given, that the elevator is moving upward at 0.5 meter per second square. Okay, so let's do it. What is the first force that's going to act on the person? So let's say The first force that we are going to show on the person is tension, okay. The second, of course, the weight of the person, which is 70 kilograms, so it's going to be 70 G. What is the third force? Is the normal contact force, which you may write as N or Fn, whatever you wish. So every time I'm writing tension as T, you can also write it as Ft. Keep that in mind, because that is something that you might see in the questions. Or you can write it as N for normal contact, or you can write it as Fn. Okay, so I'm writing T and N for now. Okay, now let's draw the free body diagram of the elevator. So whatever force this elevator is giving to the man in the upward direction, remember Newton's third law, we will show the same force. We will show the same force on the elevator in the downward direction. This is the action and reaction pair that we always talk about. Now, the next force is the force of gravity, that's going to be 30 G. And is there any other force? Yes, there is the force of tension. Why? Because this thing, this whole handle of the elevator is also part of the elevator, and we can clearly see that the rope is going to pull this elevator in the upward direction. So the acceleration of this is A, and this is also A. So this time they both are moving together. Okay, so it's very different from the first question that we did. Okay, now what should we write? We will write first N plus T, I'm writing it for the man, minus 70 G equals to 70 A, and the value of A is 0.5 meter per second square. So draw the forces on the person, that is done. Draw the forces on the elevator, that is done. Now the elevator accelerates, find the normal force on the person from the elevator. Okay, now we should write the free body diagram, the equation for the elevator, and what should it be? So it is going to be 30 G plus N minus T. Why so? No, in fact the opposite. T minus 30 G minus N equals to 30 A, and the value of A is 0.5. So what are these equations? These are the force equation, that net force is equals to ma, which is the Newton's second law. This is what I am applying, since both are going in the upward direction this time. So net force upwards for this is like N plus T minus 70 G, and for this T minus N minus 30 G. Now we first, what do? Let's say we first add the two equations, or we can subtract the two as well, whatever is correct, because you know we want the value of N. The force that the person exerts on the elevator floor is find the acceleration. So that's the second part, we'll do it later. First we have to find the value of N. So let's do this. First add the two equations. Okay, so this will make it 2T, because N and N will cancel out, and this is going to be minus 100 G, and that is equal to what? 70 times 0.5 is like 35, and 30 times 0.5 is like 15. So this is 35 plus 15, that is 50. Alright, so that is 50. So 2T equals to 1050. So T is equals to 525 Newton, isn't it? This is going to be 525 Newton. And now if we know the value of T, we can also get the value of N. So very quickly let's do that. So T is like 525 minus 300, I am taking G as 10, minus N, and that is equals to 15. So N becomes 225 minus 15, that is 210 Newton. So that is the value of Fn, okay, the normal contact force. That is what they are wanting us to find out. Very easy, but a little different from the questions that we had done, because in previous both questions, if one was ascending, the other was descending. Here the question is a little unique because both are ascending. Why is that happening? Because you know the string continuously is being pulled and it is being shortened, and that is why continuously both the elevator and the man both are rising. Copy this down, compare it with your solution, then we move forward. Alright. So, let us do this again. Now, the force that the person exerts on the elevator floor is 200. So, what was it in the previous part? So, it was like 210, but now it is 200. Find the acceleration of the elevator. So, I think this can be easily done. The only thing that changes is instead of n to be 210, we will now write it as 200. So, let us use the same equations again. So, first for this one, so this was n plus t minus 70g equals to 70a, and for the elevator it was t minus 30g minus n equals to 30a. Now let's subtract the two equations. Maybe we'll get rid of t straight away, and if we do that, we are getting 2n. So I'm subtracting the two equations. All right, so this is equation 1 and this is equation 2. I am subtracting the two. So what will happen is, this is 2n and this will become t minus t will become 0. All right, try it, solve it for yourself first. All right, so 2n, and when we are subtracting now, so this is 2n, t and t will cancel out. This is going to be minus 40g, all right, and this is going to be 40a. Now, what value of n has to be taken? It is 200. So, this is going to be 2 times 200 minus 400 equals to 40a. So, 400 minus 400, what are we getting? A is equals to 0, which means that this person is going to be in equilibrium. So, as long as he is holding the rope like this person is going to be in equilibrium when n is equals to 200. If he lets it loose, then he will start descending. If he applies more tension than this, then he will start ascending. We can also calculate the value of t if you want. Now, because A is 0, so t becomes equal to 30g plus n, and since n is 200, so t is 500. So, what is the force he is applying on the rope? That is 500. If he applies more than 500, then he will ascend, as was the case in the previous question, in the previous part, when it was 525. If he applies less than 500, then he will start descending, and if he applies 500, then he will be able to maintain himself in this particular position. So, very interesting question. A lot of things involved in the same question. We had tension operating, we had normal contact force operating, and it was a case of equilibrium and not in equilibrium also. And I hope you are able to understand this. Copy this down and then we move forward as usual. Alright, so now let's move forward and discuss another type of force, that is the force of friction. So, you obviously would have an idea of what friction is. Just take an example, again the table in front of you. Let's say you have a table in front of you and you apply a force on it to move it forward. Now, imagine if the force is way too small. Would the table move? I think no, right? The table won't move. That means the net force on the table is 0. But you have applied a force. Then how is the net force 0? So obviously there is a force that is applied by the ground that stops it from moving forward. That is friction for you. So friction is a force that acts between two objects which are in contact with each other, and we are precisely talking about friction in solids. In liquids or gases, it is by another name called the drag force, which we will deal with in the upcoming classes. So I will read it out to you first. Friction is the force that occurs between two surfaces in contact, as I said. Cause. So now it was earlier believed that no matter how smooth any surface appears, it has, roughness or abruptness at the molecular level. So this causes the interlocking of hills and grooves. So if I may show you the diagram, like somewhat like this. So there are like deformities, there is like abruptness in the surfaces that causes interlocking of these hills and grooves. So when you try to move one thing over the other, this interlocking prevents that or let's say tries to prevent that. So that is called friction. Okay, so this is what we used to believe earlier, but now with, since physics is evolving, now we know that, friction is caused by the electromagnetic interaction, that is the charges of one surface interact with the other, that causes friction. Okay, we'll talk about that. First, let me read it out to you. So it was believed that interlocking between the hills and grooves between the two surfaces in contact causes friction. It's always in the opposite direction of the net applied force. So right now we are talking about friction when the object is at rest. So that is called static friction. So static friction is like when you are pushing the table, let's say like this, the friction is going to act on the table in the opposite direction. So if you apply the force on the table to the right, friction will act on the left side. If you apply the force on the left, friction will act on the right side to cancel that out, isn't it? Now, what factors affect friction? So imagine this. Let's say you apply a force, table is not moving. You apply more force, table is still not moving. That means friction is able to counter the force that you apply. But at a point, there will be a limit to that. Okay, so that limit basically means the highest value. Basically means the highest value friction can acquire. Okay, that basically means the highest value friction can acquire. What decides on that highest value? So imagine if the table is heavier or lighter. So if let's say there is this table and you apply a force, and let's say hypothetically on 20 Newton the table starts moving. Okay, so you would say that 20 is the highest value friction can achieve over here. Now imagine you keep a lot of books on that table, let's say 20-30 books on the table. You would like to believe that the table has become heavier in that sense, that it is now applying more force on the ground. Now you would see that the table won't move in 20, maybe it will start moving in 30. What does that tell you? That frictional force, the limit of frictional force that it can achieve is directly proportional to the normal reaction force. Next, it depends on the nature of the surfaces. So let's say that table was moving with a force of 20 Newton. If the floor is having some kind of texture, if you change the type of floor, or if you change the type of texture of the bottom of the table, won't that force be affected? Yes, of course. So it depends on the nature of the surfaces in contact. You can simply call it rough surface or smooth surface. So rough surface means friction would be more, smooth surface means friction would be less. That is how we define roughness and smoothness in terms of friction. And to reduce that, we can use lubricants, we can use oil, and we can also reduce this friction, right? So presence of any liquids or lubricants reduces the frictional force between two surfaces. It's independent of the surface of area in contact. So this is very important. Let me give you an example. Let's say you have a block which is cuboidal block and you place it like this, okay? And let's say hypothetically you need 20 Newton force to start it moving. That means the highest value friction can achieve is 20 Newton. Now what you do is you change its orientation and you make it vertical, okay? Now what have you changed? Is the mass of the brick or the block changed? No, but the area of contact, that has changed. Now if you apply a force to start it to move, you would be surprised to know the force will still be the same. What does that tell you? That tells you that friction does not depend on the area of contact. Whether you have more area or less area, as long as the normal contact force is the same, which of course would be the friction, the highest value friction can achieve, which we call as the limiting friction, will also be the same. Keep that in mind, alright? So these things you have to note down about friction. We are starting with a very new type of force which you might not have dealt mathematically in your previous classes, but it's going to be very interesting because it is a very situational based force. So that is why there is a lot to learn in friction, but first copy down the important stuff, then we move forward. Alright, so we are discussing solid friction, and now let me tell you that we will divide this study of friction in two parts. Okay, what are the two parts that we are going to talk about? One is static friction and the other is dynamic friction. Keep that in mind. We can also call it as the kinetic friction. So imagine when you are applying the force on the table and the table is not moving, then the friction that the ground is giving to the table is called static friction. So we would like to say that static friction is the friction that is existing between two surfaces when there is no relative motion, when there is no relative motion between the objects. So if the table is not moving, then it is static friction. Think about when you apply more than 20 Newton and the table starts moving, then the friction becomes dynamic. So dynamic friction exists when the surfaces or the objects are in relative motion, Keep that in mind, all right? Static friction and dynamic friction. These are the two types of friction which you need to understand before we proceed with this particular topic. Write this down: friction, two types, static and kinetic or dynamic. Okay, now the next thing. So factors affecting friction. So we have talked about it, that frictional force is proportional to the normal reaction. It depends on the nature of surface, but it is independent of the cross section area that we have talked about. But one thing that now we wish to talk about, that the frictional force, the highest value frictional force acquires, is proportional to the normal contact force. As I was telling you, that when there were no books on the table still moved easily. But when you kept a lot of books on the table, it did not become heavier in that sense. It did not add mass to the table, but it started pushing the table towards the ground with more force. That is what we try to say here, that the frictional force Ff is proportional to the normal contact force. And then the constant of proportionality, which we are denoting by mu, is called the coefficient of friction. Called the coefficient of friction. Keep that in mind. All right. So this is the next thing, that how do we quantify friction? Frictional force is proportional to the normal reaction and the constant of proportionality is called the coefficient of friction. Okay. Now let's talk about static friction. It is the type of friction that exists between two surfaces when there is no relative motion between them. It is always equal and opposite to the net applied force, isn't it? So imagine when you apply 2 Newton on the table, how much friction do you expect? The ground is going to provide 2 Newton because the table is not moving. When you apply 3 Newton, friction again becomes 3 Newton. When you apply 20 Newton, friction again becomes 20 Newton. So till the limit is achieved, can we say that for static friction, the value of friction is equal and opposite to the net applied force? We can denote it by a vector quantity, so we are putting it an arrow here. Okay, so minus sign is indicating that till the limit is achieved, applied force and friction both are equal and opposite. Don't worry, we will do a mathematical problem on this and then we will understand. Okay, now once the relative motion starts, then we start calling the friction as dynamic friction. So now do you see a difference here? That the highest value friction achieves, we call this as the limiting friction or limiting value of static friction. What do we call this? Limiting value of static friction. And this is called dynamic friction. What is the difference? Here we have used coefficient of static friction mu s, and here we have used coefficient of dynamic friction mu d. It is believed, imagine when you were pushing the table and let's say at 20 Newton it started moving. That means the limit static friction can achieve is 20 Newton. But once it starts moving, the friction slightly reduces. Why so? because this interlocking, if we may relate it with that, because most of the times this theory works where we imagine friction to be caused by the interlocking. So this interlocking is more firm when they are at relative rest. Once they start moving against each other, the friction slightly reduces. So let's say if the limit of static friction was 20, maybe dynamic friction will be 18 or 19 for that matter. So can we say that the dynamic friction is slightly less than or equal to the limiting value of static friction, is less than or equal to limiting value of, let me again revise this for you, that dynamic friction is when the motion has started relatively, and static friction is when the relative motion has not started. The highest value static friction may achieve is called the limiting value of static friction. Okay, we will only understand this when we do a numerical on this, how exactly this is operating. But keep in mind that we have two different types of coefficient of friction. One is called the static, which is valid for the static friction, of course, that is mu s when there is no relative motion, and this one is valid when there is relative motion. Okay, copy down the important stuff, then we use this and you will understand. All right, so now this, I would like to explain the whole situation to you by taking a practical example. So let's say we are applying a force and we are gradually increasing it. Okay, we are gradually increasing this force, and obviously the friction is going to act in the opposite direction. Okay, so we can denote it by FF, let's say the frictional force. Okay, now imagine when you apply 1 Newton on the box or the table, the friction also becomes 1. When you apply 2, friction becomes 2. When you apply 3, friction becomes 3. So can we say that, let's say we'll take a straight line here. So can we say that initially the graph should be like this? Why should it be like this? This is a graph that is of slope 45 degrees, exactly bisecting. Why? Because if your force is like 1 Newton, friction is also 1 Newton. If magnitude of your force is, let's say, 10 Newton, then friction is also, this is not drawn to the scale, so this is also 10 Newton. So these coordinates, I am just wanting to give you an idea that if you apply 1, friction is 1. If you apply 10, friction is 10. This will continue up till, let's say, 20. So what have we decided here? Let's say the limiting value of friction is 20 Newton. So till 20 Newton, the applied force and friction both are equal, and friction is able to counter this force. But let's say once you go beyond 20, let's say 21, immediately the box will start moving, and it will start moving with a jerk. Why? Because immediately the friction drops a little. So if it drops a little, let's say like this, and its new value becomes, let's say, 18 Newton, then beyond this value, what's going to happen? It will become fixed. So we will say that friction has become dynamic. Doesn't mean that friction has stopped operating. Imagine even if the table is moving, friction is still acting, right? So here we are in the dynamic mode. Isn't it? The friction is in dynamic mode, and here it is in static mode. And the highest value static friction can achieve is called its limiting value. Okay? So don't ever imagine that static friction is always equal to this. Static friction is situational. It balances, it adjusts its value according to the applied force. But once motion starts, then the friction value remains the same. Okay? So are you able to realize, let's say, that initially how friction is increasing with the applied force? So if I may ask you that the table is in front of you, what is the friction acting on it right now? The answer would be 0, because you have not even applied a force. So there is no need for friction. So friction is a self-adjusting force. It will keep adjusting its value as per the force applied by us, right, or the net force experienced by the object. But then there is a limit which is called the limiting friction. I hope you are able to grasp what I was wanting to explain here. Static friction and dynamic friction, and why does this graph look like this. Copy this down, and again 20 and 18 was just an example, otherwise the limiting value is decided by the coefficient of friction and the normal contact force. Okay, and sometimes this difference might be too small. So for example, if this is 20, then dynamic friction might also be just very close to 20. In that case, we assume that coefficient of static and coefficient of dynamic friction both become just equal. Otherwise, we can say that coefficient of dynamic friction is always less than coefficient of static friction. Only in some cases the two might be very close to each other. In that case, we assume that the line will continue here rather than this drop. So this drop won't be there. Okay, again let's apply this in a numerical for a better understanding. All right, so now apply this in a numerical. You copy down the numerical, or you try it first and then see the solution part. I will wait, and you pause the video, copy down the question, try it, and then see the solution. Okay, so now this is a block. The mass of the block is given to be 4 kilogram. So let's draw the free body diagram. 4G is acting in the downward direction, all right, and the normal contact force Fn is going to act in the upward direction. So let's take gravity as 10 for now. G is equals to 10 meter per second square, but you can also solve it by using 9.8. Then the answer will be slightly different. Let's say in the question we assume that the value of Earth's gravitational field strength is 10. All right, so Fn is equals to 4G. Why do I say so? Now you obviously know the block is in equilibrium. It is in equilibrium in the y direction. So it's not moving in the y direction. So Fn is equals to 40 Newton. All right. Now what are we doing? We are applying a force which varies with time as F is equals to 2t, right? And the coefficient of friction here is given to be 0.5. Now you might wonder that there is only one value of coefficient of friction, which obviously means that both mu s and mu d both are taken to be the same. Okay, so let's calculate the limiting value of friction, which of course is mu n, and that is going to be 0.5 times of 40, and that is going to be 20. So till 20 Newton this block won't be able to move. So now imagine, let's again draw that line. So initially till the frictional force becomes 20 Newton, okay, this block is not going to move. So what is the time corresponding to that? Since F varies as 2t, so 2t is equals to 20, so t is equals to 10 seconds. Okay, so till 10 seconds the friction will increase, and you apply 2 Newton, the friction will become 2, you apply 4, friction will become 4, you apply 10, friction will become 10, and this will continue till 20. What happens after that? After that, friction will remain fixed at 20. So it won't change its value. Why? Because then the block starts moving and the friction becomes dynamic, which is a constant value. So can we write here the friction is static and here it becomes dynamic. In this case, you don't see a jump downwards. Why? Because there is only one value of mu given. If there are two different values given, then always mu d is slightly less than mu s. So I hope you got this. The only difference is now we are plotting the frictional force versus time. All right, next question. Let's do one more. Figure shows a block at rest on a rough table. The block is connected by a string that goes over a pull to a second block hanging, right? Then draw the forces on each body. So here we only have to draw the free body diagram, very quickly, the force acting on this is, let's say, m1g, and this is the tension force acting on it. So what are the two forces acting? Weight, that is the gravitational force, and tension, right? Or we can write T, or we can also write this as Ft. Okay, what about this one? Ft is acting forward, let's say m2g is acting downward, normal contact force due to the table, and since this block has a tendency to descend, so this block will have a tendency to move forward, and to avoid that, frictional force will act in the backward direction, isn't it? So are you able to correlate with the free body diagrams? I hope you understand what free body diagrams are all about now, and all the forces were to be shown, and we've wonderfully done that. And let's do another problem like this, where we are utilizing this free body diagram to predict something. Alright, next. So a box is pushed across a level floor at a constant speed with 280 Newton. So focus on the word constant speed. So since it is a constant speed, that means acceleration is 0. Okay, so this is being moved with a constant speed, and we can say that the net force is 0. Alright, the force is applied at 45 degrees to the floor. Let's say this is the force F. Let's resolve it. This mass is given to be 50 kilograms. So let's draw the free body diagram. So this is going to be 50g, and let's resolve this force. So I hope now you understand how to resolve the force. So this is going to be F cos 45, and this is going to be F sin 45. Alright. What is the other force? The other force is due to the normal contact force from the ground. Now imagine you are pushing this block forward, so friction is trying to prevent that, and therefore it is acting parallel to the surface in the backward direction, isn't it? So I hope you are now comfortable with how to draw free body diagrams, and if any force is like inclined, then you resolve it, you take its y and x components. Alright. So first thing that we have to calculate is the vertical component of the force. So that is easy, because this force is like 280 Newton. So let's do this calculation very quickly. So 280 cos 45 is like 1 by root 2. So let's divide it by root 2, and this value is turning out to be 198. 198, and so will be this, because in case of 45 Newton, in case of 45 degree, both x and y value will be the same, because cos 45 and sin 45 both are equal in value, that is 1 by root 2. Alright, so the vertical component of the force, the answer I hope you can easily predict, is going to be 198 Newton. The weight of the box, alright. So what is the weight of the box? So answer is going to be mg, and that is going to be 50 times 9.8, which is going to be 490 Newton. But if we have to answer the normal contact force, so let's do that also. The horizontal component of the force is again 198. Here both are equal, the reason being because of 45-degree angle. The coefficient of dynamic friction between the box and the floor. So let's calculate the normal contact force, which is the force with which this is going to push the ground, right? That is what we are calculating as, you can call it as the apparent weight, right? So what is the apparent weight? Fn is equals to, so we are going to use the equation in the y direction. So in the y direction, what are we going to write? We are going to write upward force is Fn minus downward force is 50g minus downward force is 198, and this is equal to 0. So this makes this Fn is equals to 490 plus 198. So let's add 490 plus 200, that is, let's say 690, subtract the 2, so it's going to be 688 Newton. All right. Now the horizontal, in the horizontal direction, so this equation I have written in the y direction. In the x direction, it is given that You know, the block is moving with a constant velocity. So can we write that 198 minus FF is going to be 0. So that means the frictional force is equal to 198. Now think about this. We have calculated the value of Fn, we have calculated the value of Ff, and now we know that frictional value is equals to mu times Fn, isn't it? Because it is moving, right? So we have to predict the coefficient of friction. What is the value of friction? 198. What is the weight? So I'm again repeating, weight is the force with which anything pushes the ground. That is how weighing machines measure weight. So that in that case, the answer has to be given as 688, right? So mu is what we don't know, and let's put this value as 688, and let's solve this value for mu. So it's going to be 198 divided by 688. So the value of mu that I am getting is 0.288. If I round it off to 3 significant digits, I am getting 0.288. That is the coefficient of friction. So today we started off with pulley system, how a pulley operates, and then we talked about how friction operates, what causes friction. Again repeating, the easier theory to believe is that friction is caused by the roughness, but you know, if you dig deep into this, you will realize that friction is not easily judged just by the roughness. It is a result of the adhesive forces, that is the electromagnetic forces between the two surfaces in contact. And this also causes obviously wear and tear of things like of machine parts and tires. But at the same time, friction is very important for us because it is only the frictional force that helps us move forward. It is only the frictional force which helps us to, you know, hold on to things. So in that ways we can say friction is a necessary evil. We need it. At the same time, it is a problem. Many a times it causes heat loss, energy loss. So imagine if you keep rubbing your hands like this, then frictional force is going to produce heat, and sometimes it causes unnecessary energy loss. So that was my attempt to start with how friction operates and pulleys operate. Next, we'll keep coming up with such videos, take more questions to gain more confidence, and then ultimately we will start doing the previous year questions. That is where we will apply all the knowledge together. Alright, so keep working hard, and I will see you next time in the next video. And that's all for this one. Revise everything before the next video. That's all. Bye bye. Take care. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.